Okay, so it's a course which is called Batalin-Vilkovisky quantization. It's a mathematical physics course, which should be interesting to students both in more physics program and more mathematical program. So what it is about mathematical foundations of gauge theories. So I'm sure you all heard about this and even study some of them. So it's a very important concept in modern fundamental physics, because according to what we understand, the fundamental interactions are mediated by so-called gauge fields. So these are fields which have certain degeneracy. So they are like described in terms of over a complete set of variables, interactions. So this gives us gauge fields. And these are the examples, of course, electromagnetic field, Young-Mills field, gravity, all interaction fields in standard models, and also some alternative theories like string theory, etc. They are also gauge theories. So from perspective of fundamental interactions, it's important to understand the first principles behind these theories, but also these ideas of gauge invariance and the idea of gauge fields turned out to be very fruitful from a mathematics point of view, and has brought to mass many interesting ideas which were then developed. There are very deep links between gauge theories and topology and homological algebra and algebraic topology and many other areas of modern mathematics. For instance, what's called topological field theories are also like extreme examples of gauge theories. So I believe these words are sufficient to justify why we want to study it. And what this Batalin-Vilkovisky formalism is what gives us a systematic mathematical framework to study these gauge theories. First of all, the original problem why this type of approaches were developed was the problem of quantization, because naively it's not immediately clear how to quantize a system with gauge freedom, because if you just apply naive canonical quantization or naive path integral quantization, it just doesn't work. So you need to take care of these extra degrees of extra variables. They are not physical degrees of freedom, but still they are present in the description of the system. And you need to invent some kind of methods. There are different methods, and the present day perspective is that it looks like probably the most fundamental point of view on these issues is precisely this Batalin-Vilkovisky approach, from which other ones can be derived if you want. Sometimes it's an overshoot, sometimes it's too powerful. For instance, if you just want to quantize Maxwell field, right? The very first example of gauge field is a Maxwell field, right? We want to describe electromagnetic field in terms of one form potential, right? A mu of x. And we know that physically what we observe the electric and magnetic field, which is a field strength, which is F mu nu, which is d mu a nu minus d nu a mu, or mathematically in more refined language. We write this, right? A is a one form, and F is a two form. And of course, the map from A to F is not one-to-one, right? Because it has a kernel. So for instance, if we replace A with A plus d lambda for some function lambda, then f is unchanged. And Lagrangian, which we know the Maxwell Lagrangian, f squared d for x is also unchanged because it depends on f. So this is the very first and the very simple example of gauge symmetry. And immediately here you see that in order to write down Lagrangian formulation for Maxwell field, we can't just stay with f. Of course, we can write Maxwell equations in vacuum, for instance, just in terms of f, and there is no need to speak about gauge symmetry. But if you want Maxwell Lagrangian, or if you want interactions to describe in Lagrangian terms interactions between electromagnetic field and currents, that's when we want to add this kind of term, right? We need to d for x also. We need to work in terms of A. So it's kind of unavoidable when you study interactions. It's kind of unavoidable to hit gauge fields. There can be better explanations, more systematic of this phenomena. But let's don't get into it for the moment, because we want to first study something basic. The idea, usually, if you want to understand something, it's a very good idea to start with something simple, right? Typically, that's what we call toy model, right? A very simple system or class of systems which are simple enough not to waste efforts on technical details and specific features of one or another model, but to concentrate on the main idea, to maximally simplify. So in my opinion, a good toy model to study this story are so-called constrained Hamiltonian systems. Constrained Hamiltonian systems. These are how gauge theories appear in the Hamiltonian formalism. So we will talk in more details about this, but this is roughly speaking what gauge systems are, mechanical gauge systems are from the Hamiltonian perspective. The point is that the usual Hamiltonian description doesn't work for gauge systems, and you encounter something more general, and these are precisely constrained Hamiltonian systems. To be precise, these systems are not necessarily gauge. There are so-called second-class constraints which are not associated to gauge symmetry, but still they are very similar, and still they often show up in field theories when we study field theories. So it makes sense to study them together with constraint system associated to gauge fields. Of course, we start with mechanics to avoid complications related to field theory, because everything is finite dimensional, easy and understandable. And our aim is to first have some recap of basics of Lagrangian and Hamiltonian formalism, and then go for constraint systems. Just to give you an idea what kind of systems, what kind of meaningful physical systems belong to this class, let's consider, for instance, relativistic particles. So example, just to give you an idea what kind of system we are talking about. Example, for instance, relativistic particle. So what it looks like, we know if it's a massive particle, then we know that action of a particle. So the trajectory. So we have time, we have space coordinates, right? And then we can write our action like this. So S of x is what? Something like minus mc integral dt x dot squared to power half, right? I'm not sure if the coefficient is right, but something like this. So that's the action of free relativistic particle. If you want, for instance, if it is charged, if you want to couple it to background electromagnetic field, you get extra terms, but let's just concentrate on this. So it's a usual system. There is nothing special about it, but of course it's not very convenient to describe it in these terms, and the reason is as follows. First of all, it's not clear what is limit m to 0 means. So how to describe massless particle? Because action is proportional to mass, you can just set m to 0. Second, it's also not convenient to have this square root. Even if we are interested in a massive particle, it's not convenient to have the square root because action is quite nonlinear. It's not what we usually want from a very simple system, because we know how particle moves, right? It just these are just straight lines, right, in 4-dimensional space. So the answer is to rephrase it differently, and probably the easiest, I will immediately write down something what is called Hamiltonian action for the same system. In this case, it is going to depend on x mu. Now it's also going to be manifestly Lorentz invariant, p mu momenta, and then it looks, and in fact it also depends on something else called auxiliary variable, Lagrange multiplier, and then it looks like this. It looks like a standard Hamiltonian action, p mu x dot mu. Maybe plus is better, so it doesn't matter. P squared minus m squared. So this is the action, and you see, it has p squared. Now it's Minkowski p squared. So p squared is eta mu nu. It's eta mu nu p mu p nu. So the action is manifestly Lorentz invariant, right? Because all indices are contracted correctly. And for instance, the p squared is formed with an invariant Minkowski metric, which is invariant under Lorentz transformation. So it's manifestly Lorentz invariant, which is good. But this action doesn't have a form of a standard Hamiltonian action, right? First of all, what we know, we will recall it shortly. Now it's just to give you ideas, that in usual mechanics, if we, for instance, study non-relativistic particle, the action usually looks like this. It's S of, let me put vectors to distinguish non-relativistic case. It looks something like this: P x dot minus h of px, where h is Hamiltonian, right? dt. This is Hamiltonian action, right? Usual one. So first of all, we see that coordinates and momenta, they come in pairs. They are conjugate. So from this term, you can read. So you can read the symplectic structure as or Poisson bracket at the end of the day, according to which each coordinate has an associated momenta. So coordinates came in pairs. Of course, if you parameterize in a standard way everything, but here it's not the case. You see, we also have coordinates, we also have momenta, but we have something extra. This is called Lagrange multiplier. By the way, to be really correct, we need to say that this Lagrange multiplier is not equal to 0. This condition may look strange, but if you really study it carefully, you will understand that this lambda, the geometrical meaning of this lambda, is roughly speaking like Einbein or frame field in one dimension on the timeline, or square root of a metric. So you can think of this model as a kind of toy model for gravity. And this lambda squared is roughly speaking metric, and we know that metric must be non-degenerate. That is why lambda is required to be non-vanishing. Otherwise, the equivalence between these two is not going to work. And in fact, they are equivalent. This action and this action and this action, they are equivalent. And to see this, what we need is to actually eliminate p momenta, because, for instance, how do we show that this action, in case of non-relativistic particle, this action, how do we know that it is equivalent to a standard second-order action? We consider equations of motion for p. So we vary p variables, and we see that if Hamiltonian is usual one, like p squared something, then these equations can be solved with respect to p. Then we put this p back into the action, and we arrive at the usual Lagrangian form, second-order form of this system, where the action of x is integral x dot squared over 2, right? Well, with mass, at least in standard mechanics, right? The same is here, but here the procedure is two-step. So first we eliminate p mu. It's easy to see that because of the presence of this p squared term here, if we vary with respect to p, we can solve equations of motions with respect to p. Then we substitute it back, we get another action, and then we see that still there is this variable lambda, but in fact it also turns out to be auxiliary. So we then eliminate lambda. So the equation of motion obtained by varying with respect to lambda can be solved with respect to lambda. Precisely for this, we need that lambda is non-vanishing. And finally, we get to this action. So this arrow is simple, it's just straightforward, and it's a good exercise. I don't want to do it here explicitly because it's purely technical, but it's very instructive. So I very much suggest to check, show the equivalence of, let's say, this is going to be 1, and this is going to be 2, of 1 and 2. Or more specifically, what we need is the arrow, 2 to 1. Because from 1 to 2 is less obvious how to do. It's also possible, but this is more tricky. To eliminate variables is kind of easier than to add. Okay, so you see that even if we study relativistic particles, we meet systems which are not usual Hamiltonian systems. The characteristic feature of these systems is that in addition to coordinate and momenta, we have some extra variables which do not have their conjugate momenta. These are these lambdas. They are called Lagrange multipliers. And also that the action has different structure. So there is an extra term which is proportional to this lambda. So there is a term which has the structure Lagrange multiplier times something. This something is called constraint, and here the meaning is clear. It's just mass shell condition, like that square of momenta equals to mass square. And somehow one of the equations of motion, if you derived from this action, if we vary with respect to lambda, we just get the constraint equations that p squared minus m squared equals to 0. This is quite in contrast to standard Hamiltonian system, and this is a more general setup. And in fact, most of relativistic systems, they are of this type. Like the very first example we just saw, it's a massless particle, because you see this also the point is that here for this action we can set mass to 0. In contrast to this action, where we can't, here we can. And this gives us a freedom. So this approach is more flexible. This gives us a freedom to consider massless particles, for instance, in Hamiltonian formalism. Okay, good. So this is to motivate. But before really getting to these constrained Hamiltonian systems, we need a brief recap to be more careful with what Lagrangian formalism is and what Hamiltonian formalism is. Maybe it's a good point if there are to ask me questions, if there are any. Of course, it's an introductional part and you are not supposed to follow everything in details, though I'm sure that many of you actually saw all this in one way or another. But if you miss something, don't worry, we will systematically study these issues later. Any questions?
For now, no. At least from my part.
Okay, good. So let's go to then Lagrangian formalism. A brief recap. I understand that for some of you, this may sound a bit too naive. Because we're even going to talk about one-dimensional case, roughly speaking, mechanics. And multidimensional will be later when we will go to field theory. Okay, so what is Lagrangian formalism? We know that our equations of motion are typically second-order ordinary differential equations, right? ODE, ordinary differential equations, usually second order. And they can be seen as certain relations, let's say E alpha, which relate our phase space coordinates, the velocities, and accelerations, right? If it's second order. In principle, of course, one can consider higher order differential equations. So what this means, it means that E alpha is a function of 3 sets of variables, coordinates on our configuration space, velocities, and accelerations. So what does it mean that equation is satisfied? It means that we have a concrete concrete trajectory qi of t, such that if we substitute here this q dot and q double dot for this concrete function, it is satisfied. Then we say that this trajectory satisfies equations of motion. It's a true trajectory of our mechanical system. So this is a general setup. The general evolution of a mechanical system should look like this. And in order to define it, you need to give few functions of these variables to define a system of ordinary differential equations. And of course, this is not very convenient on one hand, because you need to specify many functions. You have a system of differential equations. And also it turns out that realistic physical systems, like the particle we just talked about, or Maxwell field, which we also just discussed, they have a very special equations of motion. Their equations of motion, these ODEs in the case of mechanics, these ones are determined by just one function, which is called Lagrange function, and which usually can be taken to depend on coordinates and velocities only. Of course, again, general case, it may involve second and higher order derivatives, but usually you can even restrict to this situation. So the standard definition of Lagrange function, let's start to be more geometrical. So the standard definition of Lagrange functions is that we consider space, which is Tm, where M is our configuration space, timeline. So M is configuration space.
So Tm is actually tangent bundle, right?
Yes, exactly. Configuration space. So coordinates in our examples, coordinates there are Qi. So Tm indeed thanks tangent bundle. Tangent bundle. So coordinates Qi and Vi. So what is tangent bundle? Points of tangent bundle are pairs. Point of a base plus a tangent vector there. So these Vi are just components of a tangent vector, right? And Qi are coordinates of a point which we are point on M, which we are talking about. And T is timeline. So for simplicity, well, not even for simplicity, we just take T equal R1. We don't want close timeline, so we take it to be R1. So this is a space where, let me give it another name. For some reasons, for future, I call it J1. Just a moment. I call it J1. And the Lagrange function, by definition, for second order systems, Lagrange function L is a function on this space J1. If you want or if you have a system where you need higher derivatives, then you will need to extend the space. But in most of the cases, it's enough to work with this J1. So it's a tangent bundle over M times T. Do I need to explain, because I will be using all the time this language of bundles, do I need to explain in more details what tangent bundle is, or everybody is familiar?
I think we are familiar with it.
Okay, good. Tangent bundle over M here. Okay. So what this Lagrange function gives us? It gives us a possibility to write down certain action. So if we have L, so we can say that suppose we have a trajectory Qi equal to gamma I of t. Now I'm going to be a bit careful with what depends on what to avoid some confusions, because it's important to understand. Then, of course, I will be again sloppy with conventions, because I'm sure we will have everything well defined. So, so suppose we have a trajectory. Then, given such a function on J1, we can actually build a functional. So we can associate to this trajectory the following number, well, which is, let's write it like this, which is integral over dt of Lagrange function of gamma of t and gamma dot of t. And in general, of course, our Lagrange function may depend on t as well. You see, everywhere it's same moment of time, same t. So there is a function. The Lagrange function, is defined on this space. It's just a finite dimensional space in the case of mechanical system with coordinates. So what are coordinates here? Q, V, and T, right? So, and then if we have a concrete trajectory, so invariantly gamma is a map from time to M, right? It's a trajectory in our configuration space. Then we can substitute it. We can evaluate L on a concrete trajectory at a given moment of time, where in place of velocity, we really push velocity of this gamma. And we get a function of t. So this is a function of t which we can integrate, and we disregard for the moment if the integral exists. Suppose it exists, it's not so important now. And then of course all of you know that what we can do, we can study, we have action, so we can have least action principle. Action principle. So what does it mean? It means that we deform our trajectory a little bit. So we go from gamma to infinitesimal variation, and if you want S of gamma plus delta gamma to be just S of gamma plus higher order. There's no linear term in delta gamma. So the leading term is 0. This is a usual story about variational principle. So we want our trajectory to be extremal, and this is a standard problem of variational calculus. You all had it, and you know the answer. So if you want our trajectory to be extremal, then it must satisfy what is called Lagrange equation. Euler Lagrange equation, which look like this. Euler Lagrange equations. They look like this. The nice point is they can be expressed entirely in terms of Lagrange function, right? They look like this. dl over dq, where we need to put, of course, qi equal to gamma I of t upon evaluation of the partial derivative, minus d over dt, dl over dy I. Yeah, sorry, here also yi equal to gamma dot I of t. And this, and again, the same. Here we also need similar substitution. Gamma I of t. This is 0. So if the least action principle tells us that the stationary trajectories are the ones which satisfy this equation. These are called Euler Lagrange equations. Of course, it's easier to rewrite them by introducing functions ei of q, v, and let me here put also accelerations as independent variables, because this is in general the case. And they are, by definition, are just these functions on this space auxiliary. No, I need one more notion to write it. Sorry, I will need to explain something more to write it in this form. So what is important? It is important that all the dynamics of our system is determined just by one function, L, the Lagrange function, which is a function on our space J1, which let me recall you that this is Pm times timeline. So everything is determined in terms of this function. Moreover, even the Euler Lagrange equations can be thought of as functions again on certain auxiliary space, but this certain auxiliary space is a certain extension of this J1. So somehow we really, with this Lagrange formalism, we are able to pack all the information about the system into a function defined on a finite dimensional space. It's very convenient to work with. You don't need to, for many computations, you don't need to think about infinite dimensional spaces of configurations, etc. So many questions can be easily answered. And there are no confusions. Everything is mathematically well defined. For instance, if you ask questions like symmetries, like conserved charges, conservation laws, Noether theorem, this is all nicely formulated just in terms of this space and this Lagrange function. So let's be a bit more careful with what this space is. So I introduce this space J1. But in fact, it's a very simple example of what is called, it's of course, an example of what's called jet space, or jet bundle, strictly speaking. So, of course, it's in mechanics, it's all like a toy model, but it's a good illustration, and it's a good also playground to become acquainted with these objects. So why not? So let me say a few words about these jet bundles, and then we will understand what Euler Lagrange equations mean as an object defined on a jet bundle. So let me a bit more general. For the moment, I'm still stuck to one-dimensional situation, to mechanics. So what I'm going to say is that let's change point of view slightly to be more geometrical and more general. It's going to be useful in the following. So let's consider bundle E, which is trivial in our case anyway. Over timeline, all bundles are trivial, which is T, our timeline, times our M. And we are going to think of it as a base space, and this is a fiber. That's the usual terminology of fiber bundles. What fiber bundles look like? It's like a total space, and E is called total space. Total space. So our total space is like sliced into subspaces. It's like a union of subspaces, which are called fibers. And all fibers are identical, isomorphic. And there is a space of fibers. So if we consider a new space whose points are fibers, then it's a base. It is this T. In our case, a fiber bundle of this sort, which is just product of two manifolds, it's called globally trivial bundle because it's just a product. Of course, there is a projection, pi, natural projection, canonical projection, pi, which goes from E to T, right? Because what are elements of T times M? These are pairs, right? T from T and P from M. So, and pi applied to such a pair TP gives us just T, right? So that's a standard projection on a first factor of a direct product. Is it clear, or do I need to give any further details? Are there any questions?
I think we're fine.
Okay, very good. So yeah, we have such a very simple, trivial, globally trivial fiber bundle. So there is a projection. And then we need to consider what are sections. Of course, for this concrete situation, this is exactly the same as trajectories of our mechanical systems. But this language of sections is somewhat more general and useful in wider context trajectories. So what it is, so let me still use gamma because it's almost the same. So gamma is a section. It means it's a map from T to E to the total space such that its composition with pi gives me identical map on T, right? So let's draw a picture. So again, this is our E. So this is our, let me think of it as a, this is our timeline. So what does it, and these are our fibers. So what is projection? Projection takes the entire fiber and sends it to a point on our timeline, on our base, right? So this fiber is sent to another point. But what is gamma? Gamma takes a point on a timeline and sends it somewhere to the fiber. So to each point, but to the fiber over the same point. So the terminology is this fiber, which projects to this point, is called a fiber over this point because it projects there. So section is like opposite thing. Section takes this point and gives us a point in the fiber over it. So if we do it for each point, what we get, if everything is smooth, we get a submanifold here, right? So you can think of sections as submanifolds in the total space, which like bijectively project to T. So they are one-to-one with the base. So these are sections. And of course, in our setup, because recall that E is just T times M in our simplified setup. Of course, to specify gamma, it's enough it's enough to say, so gamma of T is going to give us the following pair. It's the same T, right, for the first factor, because remember, our points of E are pairs, point of T and point of point of M. So here it's enough to say that gamma of T is T. Here I abuse notations a little bit, gamma of T, where this gamma is in the old sense. So in our trivial case, section of the bundle is just another way to say a map from timeline to our fiber M, because it's same gamma. But in general, this language is preferable. Okay, so now we understood what are sections, and we understand that in terms of sections, our mechanics looks like this. Section is a trajectory of our mechanical system. And now we are ready to define this jet bundle. So jet bundle associated to our bundle E. So jet bundle is E K. There are different jet bundles and associated to one E, and they are related by order. It's roughly speaking order of derivatives, which is in, you will see shortly. So the jet bundle of order K is denoted like this, JKE. It's again a bundle over T. Well, not only over T. What it is? It's a collection of pairs T gamma T, where T is a point in timeline and gamma is a section. Let me say by words not to introduce too many notations, section. And this notation it's an equivalence class of sections at T. So how it is defined? So what we are talking about? We are talking about pairs, where the first element of the pair is a point in time, and second element is an equivalence class of sections of our bundle. Strictly speaking, one needs to consider sections defined only around this point T. We don't need sections defined everywhere, but in our setup, it doesn't change anything. You can think of just sections in general. So what is equivalence class? Means that we need to define what is the equivalence relation. And the equivalence relation, we say that gamma is equivalent to gamma prime. So two sections are called equivalent. It means that in coordinates, although the notion is coordinate independent, but the definition is coordinate. In coordinates, dl gamma I of t over dtl equals to dl gamma prime I of t dtl for all L less or equal than k. That's where k enters. So by words, what does it mean? So first of all, what is gamma I of t? It's just coordinate expression of our section, right? So this is gamma star applied to qi, right? Recall. So our coordinates on E. On E, these are T, these are coordinates on our timeline and coordinates on the fiber qi. So in order to define such a map, we need to define functions. In order to define section, we need to define functions gamma I of t. And what is here, it's another way to write this. So you know what pullback is, do you? Or should I repeat? Should I recall?
We know.
Okay, so this is just a very useful language. I'm sure it's worth studying it. It's very simple. So pullback. Let's say, let me remind you what is this pullback. It's very general, but I will speak about I'll speak about manifolds, but in fact it's even you can think about sets. So if you have a map of manifolds, for instance, you have phi from m to n, right? So phi is a function which takes a point in m and gives you a point in n. And of course, if you're talking about manifolds, everything should be smooth. So in coordinates, all these maps should be given by differentiable functions. Okay, then there is a natural map, which is called pullback. Pullback is denoted by phi star, which is a map from functions on n to functions on m. You see the trick. So phi goes from m to n, while phi star goes backwards. That's why there is this back in the name. And of course, the definition is just a composition map. It's very simple. So what is phi star? So phi star of a function. So we let f be a function on n. So for instance, f in C infinity n. So we apply phi star to a function f. According to what we want, we are going to get a function on m. In order to define this function, we need to know its values at any point. So let's define this function. So this function phi star f evaluated at point p by definition is nothing but function f evaluated on point phi of p, right? So it's very simple, very natural. You can't find anything else, and it is defined for any map phi, and this is called pullback. Back because it takes functions on the target and gives you functions on the source. And this language is very useful. For instance, if y alpha coordinates on n and xi coordinates on m, then how can we let me do it here. I don't have much space. So how do we define map phi in coordinates? We would say that phi is given by some functions like y alpha is equal to some functions y alpha of xi, right? That's how we define a map from manifold n to manifold m in coordinates. Of course, we restrict to local neighborhoods, not to speak about. So locally, we define it in coordinates. So it's just given by some functions of x. So what is the meaning of these functions, capital Y? These are, so if we take a point with coordinates x, y of x are going to give coordinates of a point phi of x, right? That's what we usually do. But an alternative way to write it is to say that this y alpha, considered just as functions on M, are just phi star of y alpha. Because coordinates are also functions, right? So we can easily apply pullback map to them, and we obtain certain functions on X with the same index alpha, and these are, of course, precisely these functions which define our map in coordinates. That's why I wrote it here. It's exactly the same, right? So in this case, our manifold M is E, and our manifold N is T. So in order to define map, we need to say what is like Q, because T is unchanged, because it's a section, it does not act on T. It doesn't change time. It doesn't change T, but it changes, but it does something to the Q. So this gamma I is gamma star of Qi. We apply pullback map to target space coordinate functions, and we apply and we arrive at functions determining our map. Is it clear?
Yes.
Okay, good. So this language of pullback is very useful in modern things in both physics and math. The question is, and we are going to hit these sort of issues because, well, physicists implicitly they often think of often work with objects in terms of functions because these are observables, something like this, right? Functions on phase space, for instance, or something. And in terms of coordinates, because coordinates are just particular functions in terms of which you can express something. Physicists prefer not too much think about points like geometers. And that's why this language is natural in physics. Also, but in math, for instance, you can also, it happens that sometimes you need to work with objects which are not really manifolds, but still there are some algebras of functions over them. That's basically the idea of algebraic geometry, if you want. And even if it's very difficult to talk about points and maps of points, you can still think in terms of these maps of spaces of functions. This happens in supergeometry. You started to have There is a course on supergeometry for some of you, right? And that's exactly one of the instances where this idea of pullback is very useful. So instead of speaking about maps of manifolds, you speak about pullbacks, which means homomorphisms of algebras of functions. By the way, it is easy to check that phi star of fg for two functions is of course phi star f, phi star g. If it's not obvious to you, do this as an exercise. So it's a homomorphism of algebra of functions from functions on target space to functions on source space. Okay, let's get back to our jet bundle. So what we defined? We defined our jet bundle to be a bundle, again over the same base manifold, which is timeline in our case, and whose fiber, this second member of the pair, it's an element of the fiber, right here. It's an element of the fiber. It's an equivalence class of sections, and the equivalence is such that these derivatives coincide at t. Well, I should have used perhaps different notation. Let me put t naught, a particular point, t naught, t naught, t naught, t naught. Okay. So what does it mean? It means that our sections, they are not the same, not at all, but somehow they behave similarly near at point t naught. For instance, if we take L to be 0, it just means that gamma of t naught equals gamma prime of t naught, right? If we take L equal 1, this equivalence relation tells us that time derivatives, the velocity of this trajectory gamma, and trajectories gamma and gamma prime, these velocities coincide at t naught. They can be totally different at other points. We only worry about one point t naught, and etc. So of course, if we go higher in L, it means that our trajectories like touch each other. Trajectories from the equivalence class, they touch each other more and more precisely. It's like first order tangent, second order tangent, etc. So this is precisely the jet bundle. So the jet bundle of order k is something which parameterize our sections up to certain derivative order. So what are coordinates on our coordinates? Coordinates on j k of our E. Of course, we have our base space coordinates, and then we need something to parameterize values of these derivatives, right? Because each equivalence class means that all these derivatives up to order k coincide. So we can just take values of these derivatives as coordinates on the fiber. So what it means that we use here qi, let me call vi the first derivatives, and then ai like acceleration, and then we can say this is something like v, well, for third derivative, etc., until k. So these are coordinates, right? So these are just values of order k derivative of our section from an equivalence class at point t naught. So this is a natural coordinate system. And now it starts to look precisely like what we had when we talked about Lagrangian, right? For instance, we said that our Lagrangian function is a function here, right? And this is precisely J1 of E. And this can be thought of, this V can be thought of as coordinates on tangent bundle. But the analogy stops here. If you want to include high derivatives, then you get these accelerations. And they are no longer related to tangent or cotangent bundle. It's like higher order structure. And that's precisely the jet bundle, which gives a geometrical meaning to these higher time derivatives of our sections. Okay, and by definition, in general, if we are not limited, for instance, to second order system or want to consider Lagrangians, even for second order system, Lagrangian could depend on accelerations. So Lagrangian, Lagrange function is a function on jk of E. Well, for some k, of course, there is an arbitrariness. For instance, if we speak about usual mechanics, we can leave on J1 and we can say Lagrange function is a function J1, but you can equally well say that it's a function J2. The only thing that it's not going to depend on this next level coordinates A. Okay, so why this jet bundle is useful? First of all, it's an object on it's a space on which Lagrange functions live. In general, if you want, in principle, to be able to handle high derivatives. Also, it's a space which gives a careful mathematical definition of what differential equations are. For instance, a system of ordinary differential equations, let's say, by definition, it's functions. Let's say E alpha. Alpha runs from, well, depends how many equations we want, from 1 till some, I don't know, m. And so these are functions on, again, jke for some k. Again, this k depends on how high are derivatives entering our equations. And so now indeed we can define, you see, Lagrangian and system of ordinary differential equations as certain functions defined on a certain finite dimensional space. We don't need to talk about functional space. Of course, once we want to study solutions, we will really need to speak about infinite dimensional space of like sections of our bundles. Okay, but before this, we need a very important structure, because this jet bundle is very special thing. So first of all, there is a concept of prolongation. So what does it mean? If we have a section T to E, then there is we can associate to it prolonged gamma, let me just call it like this, which is a section of the associated jet bundle. So it's T to JKE. So what is this? Gamma prolonged applied to a point T gives nothing else but a pair T gamma T. Do you remember that by definition, points of our jet bundle are pairs? Point of the base here, and an equivalence class of sections. So if we have a section, it immediately gives us, at any point, it gives us a point of a fiber, which is equivalence class of precisely this section, right? So in coordinates, what does it mean in coordinates? So our coordinates are t, q, v, etc. So this gamma prolonged star on t is of course t because it's section, right? It means that t coordinate of an image of gamma has same value, right? It's a definition of section. It doesn't change. It doesn't change a point of the base space. It takes a point of a base space to a point of a fiber over exactly the same point. Then, of course, gamma star of qi is just gamma I of t. These are precisely the functions which define our initial section. And then you just get derivatives. Everything is very natural. Gamma star prolonged of t, vi is what? It's of course just gamma dot I. And the same, it's easy to see the pattern. Gamma star prolonged of AI is of course real acceleration, gamma double dot, etc. The idea is clear, right? For instance, now we know how to write down Lagrangian in this fancy language, the action. So if we are given with a Lagrangian, which is just a function on a jet bundle, then S is a functional of our section. So it associates to each section a number, is by definition integral dt of gamma star prolonged of a Lagrange function. Do you remember what we wrote when we, where was that? Yeah, here. Do you remember this formula, which you know from classical mechanics course? So action is a Lagrange function evaluated on a concrete trajectory. So you substitute q with gamma of t, you substitute v with the velocity of this trajectory, etc. if you have high derivatives, and t is the same. So this formula, now we understand it, that it is nothing but gamma prolonged star applied to our Lagrange function. And now we have an action in more invariant terms. Of course, really, let me make a small remark. For the moment, I'm not going to use this language, but there is one more improvement. If you really want a geometrical language, you should say, instead of working with Lagrange function, you should work with Lagrange form, which is, let's make it curly L, which is roughly speaking this thing. Q, V, etc. You see, you need to multiply Lagrange function by a differential of a time coordinate, of a base coordinate. Such forms are called horizontal because they only involve differentials of base space coordinates. So more invariantly, they vanish on vertical vectors. And in the Lagrangian formalism of mechanics, a really geometrical definition of what Lagrangian is to say that Lagrangian is a horizontal one form on a jet bundle. And then you really get rid of coordinates, and your Lagrangian formalism becomes coordinate free. So you get gamma star prolonged of L. Of course, what I forgot to say is of the pullback, why pullback is so nice, it also extends to differential forms. So you can just do it by prescribing the following. Gamma star of, well, for instance, let's talk about this concrete thing applied to df is just d applied to gamma star prolonged f. This extends pullback to differential forms. Of course, you can define it independently, but the simple thing to remember is that if you know how pullback acts, but you know if you have a map how pullback acts on functions, you know also how it acts on differential forms. You just declare that it must commute with the RAM differential. So it means that we know how pullback acts on forms, and we can define what, in a coordinate-free terms, we can define what is Lagrange function and what is action as a functional of section. So you see, it gives certain advantages, because if you have a formulation which is coordinate-free, you are flexible to use whatever coordinates you like. The only thing that they should form a good coordinate system. This is going to be useful in some applications. Okay, so once we understand this prolongation and what action looks like in terms of Lagrange function, we can also define what. So if we have E alpha system of ordinary differential equations, then we can define gamma. We can define what solution is, because we defined a system of equations as a set of functions, right? So gamma T to E, it's a section, is a solution if its prolongation of applied to E alpha is 0. So that's what it means. Equations are satisfied, right? So we just want to be careful. We want to distinguish differential equation as a relation between our functions and their derivatives, and differential equations as a really equation defined on functional space. You see, and jet bundle is this auxiliary space which helps to do it, and it turns out very convenient in certain practical aspects, but also it allows to avoid some confusions. For instance, I remember when I was studying some elements of classical mechanics, etc., I was always confused where we really speak about functions, where we really speak about functionals, etc. And the way to systematically avoid this is, for instance, to define carefully in terms of jet bundles. Of course, once you are familiar, you forget about this, because you can always you can always eliminate the confusion by defining everything carefully. Okay, good. So this is definition of solution, and the next thing what we have nice on this jet bundle is a total derivative. Let me just define it in coordinates, although it can be done. It can be done invariantly as well. Total derivative. So what is this? It's the following object. Let me just. It's d over dt plus vi d over dqi plus ai d over dvi, etc. times v k plus 1 I d over dvk. And at some stage it should stop for order k, because you can't differentiate any further, right? Because you don't have like next order derivatives. Well, even this term actually is not there on jk. So let me better, because this one is not there. So it should be k minus 1 and here k. Yes. I need to do it carefully. So plus dots plus v ki d over dv k minus 1i. Yeah, that's the total derivative. Why it is called like this is, you see, it's just a first order differential operator, or geometrically locally it's a vector field on a jet bundle, but the name is justified by the following property, which is what? Which is if you have f function on jet bundle, it's important, though not for, so this function should not depend on like highest derivative, otherwise there can be a problem. So let's suppose this is so. I'll comment on this just a moment. So let's do the fourth. So the statement is that if you have a section, so we prolong it, we put here star, and we evaluate it on dtf, and then it equals to gamma star prolonged of f, just DODT. So you see, it mimics the action of time derivative in terms of jet bundle. So if you have a function, we can first function on jet bundle, we can first apply total derivative and then pull it back by section, or we can pull it back by section, get a function of time, and then just take a derivative. This must coincide. The only subtlety is, for this to be really true, your k in the order of your k here should be sufficiently high. It should be greater than the highest derivative on which f depends. That's why often in fundamental treatment, people consider something what's called infinite jet bundle, just not to say these words all the time, like, well, for sufficiently high k, let's forget about it, let's just take it infinite. But together with taking it infinite, we should always consider functions which depend only on finite number of coordinates, so which means on derivatives of finite order only. That's the trick, that's the only subtlety here, but I prefer for the moment not to really introduce this J infinity as a mathematical object, though it can be preferable in principle, and in a systematic study of these objects, that's what usually is done, but let's refrain for the moment from doing this. Okay, very good. For instance, small corollary is if gamma is a solution to a system of equations E alpha, then gamma also solves their differential consequences, so which means solves dt to any power L of E alpha, right? This is very simple to prove, very easy to prove. So we know that gamma star prolonged of dt E alpha. Do you remember that dt commutes? So it's do dt of gamma star prolonged of E alpha. But this is zero, because by assumption gamma is a solution. So this thing vanishes, and then its time derivative also vanishes. So it means that you can always add differential consequence to your system. So it means, well, another corollary is that E alpha and E alpha completed by dt E alpha, or whatever, dt to some power E alpha, equivalent, are equivalent. So it means that we can always add differential consequences. Now they are again functions, we can use this total derivative to get differential consequences of our system of equations. Another corollary is that if you if L Lagrange functions then if we evaluate action of L plus total derivative, let's say some function lambda here, this is going to be what? This is going to be initial action plus what's called boundary term, right? So use this property. Use this property. So what you will get integral O dt of d over dt of gamma star prolonged lambda, right? So you get a boundary term. If your integration is over integral, then you get, so this is boundary term, right? It's difference of values at the borders of the interval, the boundaries of the interval. This is called boundary term. And as you know, if you add dt lambda to your Lagrangian, Euler Lagrange equations do not change. It's an exercise. So Euler Lagrange equations do not change if we go from L to L plus total derivative of a function. By the way, it's also a good moment to introduce Euler Lagrange derivative as an object on jet space. Euler Lagrange derivative. So by definition, again, I'll do it in coordinates, but in principle, it can be done fully invariantly and geometrically, but it's not our aim. It's also an infinite story of how to do this theory systematic and beautiful, but we just need basic facts from this theory of jet bundles. So what is Euler Lagrange derivative? Is by definition, let us define it like this. Qi in our case, by definition, this is d over dqi minus dt d over d, well, let's put here something L. It's more definite, dl over d dvi plus dt squared dl over d ai minus dt cubed dl over dv3i, etc. And because the standard assumptions, well, we always assume we work on finite jets, that L depends on these higher velocities up to finite order, this sequence stops. For instance, if Lagrangian is depends only on coordinate and velocity and independent variable time t, then only first two terms matter, right? This is a standard Lagrange equations like in mechanics, but the theory is general, and we can equally well consider Lagrangians which depend on high derivatives, but then Euler Lagrange equations, Euler Lagrange derivative takes the following form, and of course Euler Lagrange equations is just ei, which is delta L. Euler Lagrange equations determined by of Lagrangian L is just this guy, ei dl Euler-Lagrange over dqi. You see what is nice with this object Euler-Lagrange derivative is that it is defined in terms of jet bundle. You don't need to think about really variational calculus in functional sense. You don't need to vary action to quickly derive Euler-Lagrange equations. You do everything on a finite dimensional space, and this allows you to use many tricks like taking different coordinate system, developing invariant calculus, many things. So it's at the end of the day, it appears useful. And for instance, it appears very useful in field theory when you want to, especially in field theory, because in mechanics, this approach is a little bit superfluous. You can anyway think systems are simple, or you can do Hamiltonian formalisms. That's what we are going to discuss next. And somehow you don't really need this jet bundle. I just use this example as a simple setup where we can become acquainted with these structures. But of course, realistically, the applications are in field theory, where these sort of techniques are useful to analyze issues like symmetries, anomalies, interactions, and stuff like this in local. If your field theory is local, that's the technique to use it. Sometimes it is called by different names, but it doesn't change the content. Okay, very good. So we are supposed to finish at when 15:05, right? So we have 5 minutes more, especially that we started a bit later. So yeah, I think I said basic words about these jet bundles. Now we can use this language. So let's start discussing. By the way, here is one important, well, a good exercise, not so easy though. Exercise shows that the Euler-Lagrange of dt lambda over dqi is 0. This explains why these transformations doesn't change equations of motion. So if you add total derivative to your Lagrangian, this doesn't change your Euler-Lagrange equations, and this is a purely algebraic fact. Though the proof of this is surprisingly not so simple, but for very simple systems, like if you only have dependence on coordinate and velocity, it's not so difficult. Try it if you want to become acquainted with this. Okay, very good. So are there any questions? Or I should try to use the remaining minutes to say something more. Can you hear me?
Yeah, everything is clear.
Okay, that's very good. It will not stay long, I think, but it's good that for the moment it is clear. Okay, so what is Hamiltonian formalism? Of course, we know, but let's try to do a bit of systematics. So the idea is, so let's do the following trick. First of all, we start with Lagrangian, which depends only on, it's not a requirement, but it's easier to explain. It only depends on velocities, not higher derivatives. Then what we can do, we can write down Euler-Lagrange equations, which look like this. So it's dl over dq minus dt dl over dv I, right? 0. These are our Euler-Lagrange equations. Of course, the way it is written now is just an algebraic equation on jet space. To really make it into differential equations, we need what? We need to evaluate it on a section. We need to apply gamma prolonged star to it, right? But with some abuse of notations, we can say, okay, fine, but anyway, everything is determined by these algebraic equations, so let's also call them Euler Lagrange equations. These are just algebraic equations which determine a surface in our jet bundle, and in fact, geometrically, it's even better to speak about this surface as an equation, not even the functions which determine this surface. Okay, so what we can do, we can always do the following trick. We can always add new dependent variables. So the standard convention is we call, in our case, time, or space-time in case of field theory. These coordinates we call independent variables, but coordinates like q or fields in case of field theory we call dependent variables. This is a language from theory of differential equations. But in physics, these are fields or generalized coordinates and time, for instance, in mechanics or space-time field theory. Okay, so what we can do, we can always add a new variable, dependent variable, and subject it to additional equations so that nothing changes. So we can just introduce new. Suppose we started with a bundle where we had t, q, and extra dependent variable pi. But this extra dependent variable pi is totally fixed in terms of the other variables. So we just add equation pi equals to dl over dvi, right? So in some sense, this variable pi is auxiliary variable. Why it is auxiliary? Because it doesn't participate in our system, right? According to our equations of motion, is just a function of the remaining variables and their derivatives. So so this system, if we consider new system like extended, so let's call it extended system. So solutions to our extended system are one-to-one to the initial system, right? Because nothing happens in the sector of these p variables. So such variables we call auxiliary, and we say that two systems of equations of motion, two systems of ordinary differential equations, just this first one, and the extended one, where we have one more set of dependent variables and one more set of equations, they're equivalent. And indeed, they define same surface, everything is the same. This variable is completely just decouples from the rest. Okay, perfect. So we have indeed new formulation of our system by different system of equations on a different space, but equivalent. And we call it like equivalence through auxiliary variables. We can always eliminate it because one of our equations tell us that this variable p just equals to something depending on the remaining variables. So we call this auxiliary. So extended system and initial system are equivalent in the sense of elimination of auxiliary variables. But there is one trick. So we can even write it nicer, right? Because as we already introduced this variable, we can actually, what we can do, we can put it here, right? Because according to the second equation, dl over d velocity is just p. You see, like this, very good. Now, our system is even first order, right? Because nowhere you will see the derivatives of second order. So everything depends in these equations. Now everything depends on q, p, time derivative of p, and time derivative of q, which is v, right? Velocity. Nowhere acceleration shows up. So it's a first order system. And it's of course again equivalent because I just used the second equation inside the first one. Nothing has changed. So this is extended system. It's equivalent to our initial system of Lagrange equations. What's wrong with it? It's not Lagrangian. naively at least. It's not Lagrangian. It's difficult to write down nice Lagrangian which generates these equations. Well, it's possible in principle in some sense, but let's not get into it. There is nothing nice. But we prefer to work with, because we know it's very nice when all our equations of motion are encoded in just one function. And the thing is that under some conditions, actually, if we look carefully at this extended system, variable v also is auxiliary. Is auxiliary if this equation, the second equation, can be solved with respect to p, with respect to v, sorry, with respect to v. And this is, of course, the Legendre transform, which we studied in mechanics. So what I'm saying, if Legendre transform is invertible, then variable v in these equations is also auxiliary. We can eliminate it. So because second equation can be solved with respect to v. And this is, once we eliminated it, we are going to get what's called Hamilton equation, which is first order equation, which involves only q and p and not v. But this we are going to discuss carefully next time, and then we will be ready to get to constraint systems. So thank you very much. Are there any questions?
Yeah, I have one question. So you introduced us the Lagrange form previously, and I have a question. So usually, like in physics, so we know that Lagrangian is like two Lagrangians are equivalent if their difference is the full derivative of time. So can we introduce some kind of homology in this Lagrangian formalism to say that physical states lives on the homology of this?
Oh yeah. But that's exactly how it works. But it's so in this term, that's called variation. This is called variational by complex, where Lagrangians are, in this sense, they are cohomology of horizontal differential. Yeah, that's more. But for this, you need more technique. We will touch a bit of this, but much later, because it's actually useless, nearly useless in mechanics, but it starts to be useful in field theory, and at more advanced level, I hope we will have time to touch a little bit these subjects.
Okay, thank you.
Okay, so there is regarding the course. So there is a kind of notes, lecture notes, which I'm going to share with you, but there are typos, and they are not maybe one-to-one with what I give now, but still they can be useful. And they also contain some problems. I also give problems, same or different, on lectures. And I think after a couple of seminars, after a couple of lectures, we will have to organize seminar, because it's important to solve problems and to do and to discuss details. I think it's better as I am away now and I can only do Zoom. I hope I will give few lectures in person, but this is going to be in April only. But I asked our colleague Dmitry Rudinsky to maybe give a few seminars. It's probably better to do it in person than by Zoom. But for this we need a few problems. First, to discuss them on seminars. So we should think of time. I don't think we need seminar each week. Maybe each another week, or even less. At least the first one, I would suggest to have a seminar like in a couple of weeks or so. Even next week, next Friday is gone, right? So then maybe even in 3, because it's It's February 23rd. It's a public holiday, if I understand correctly. So maybe in 3 weeks. But anyway, I advise you to solve problems. It's important, and it's also a part of exam, let's say. Even if we don't officially have this zachot, or I don't know what's the name, but exam we do have, and for exam I definitely want you to present some of a few problems from different part of course. So it's better to do it in advance, not to have troubles, and it definitely should help you to understand what's going on. So please don't forget about problems, and see you looks like in 2 weeks. Anyway, we have a good contact over Telegram chat, so if something changes we can always coordinate. So thank you very much, and see you next time.